So, we saw the various equivalents of spectral theorems, versions of spectral theorem for self-adjoint operators, and in the last class we had written down some result about the spectrum of an operator and connection with the support of the measures that come up in the spectral measure version of the spectral theorem, and also the resolution of identity, right. So, let me write that again because I want to explain certain things before we go ahead with the proof. So, if you remember, we had proved one part of it, we still have two more parts of it to prove. Okay. So, let us start. So, the theorem we had earlier was, so A be a bounded self-adjoint operator. Okay, so, it is bounded self-adjoint. So, we have all the details now about the spectral theorem and various versions of the spectral theorem and so on, right. So, the theorem was that the following sets are same, right. Okay. So, what is it? 1 sigma A. So, sigma A is the spectrum of A, right, spectrum of A, right, all those lambda such that A minus lambda is not invertible, right. 2. So, something you should remember about the spectrum is that it has nothing to do with all those measures. Well, the measures we construct are independent of the definition of the spectrum, right. Anyway, I will expound on that when we reach there. The set of points of increase of the spectral resolution of increase of E lambda. What is E lambda? E lambda is the resolution of identity for the operator A, resolution of identity for A, right. We know that it exists. So, the set of points of increase of E lambda. So, wherever E lambda increases. So, what does that mean? That is all those points lambda naught such that for every epsilon positive, right, E lambda naught minus epsilon is not equal to E lambda naught plus epsilon, right. So, those are the jumps for the spectral resolution, right, or the resolution of identity E sub lambda. 3. So, the third one is what I want to actually explain a little bit. The support of the spectral measure, for A. Okay. What does that mean? That is you look at support of all those measures mu sub n and look at the union over n and take the closure, right. So, here the notation says that we identify the Hilbert space as a direct sum of L2, right. So, the Hilbert space H is identified as direct sum of L2 of let us say the real line. Well, it will not be the real line, it is actually minus norm A to norm A, right. We know that, but we will not bother about it because the support is there. So, d mu j, right, over j. So, we identify H in that form and you look at the support of these measures mu j, take the union and take the closure, that is the spectrum of A, that is the assertion, right. So, before I go ahead with the proof, we proved one part of it, I will remind you of that. But before we go ahead with the proof, look at the third assertion again. These measures, remember that the measures are not unique, right, because first we prove the cyclic case and then we use the usual method of generating cyclic subspaces, look at the orthogonal complement and going ahead, right. So, the measures mu j's are constructed by looking at those cyclic measures and appropriately defining a continuous linear functional on the space of continuous functions, right. That is how the construction went. Now, there is no particular way of choosing these vectors. So, I can on the Hilbert space I can take some arbitrary vector, look at the cyclic subspace generated by that vector and then construct the first measure mu 1. Then I go to the orthogonal complement, choose one vector from there and then generate the cyclic subspace again, construct the measure mu 2 and so on, right. So, the way mu 1, mu 2, mu 3 etcetera are constructed will depend on how you chose these vectors, right, first. So, how you generate these cyclic subspaces. But the spectrum has nothing to do with any of this, right. The spectrum of the operator is well defined and has nothing to do with the order in which we choose these measures and or vectors and so on, right. That is sort of independent. Nevertheless, this union, the closure of the union of the support of these measures we construct, does not matter how we construct, which order we construct them etcetera, you still get the measure, you still get the spectrum, right. So, even though the measures are not unique, the measures are going to be still supported on the spectrum of the operator. Okay. In a sense, it is not very surprising because you are realizing your operator as multiplication by x, right, on the spectrum, right, or on or on minus norm A to norm A in that set. Now, when you have multiplication by x with respect to a certain measure, the spectrum of that operator is the essential range of what you are multiplying with, right, essential range of the function x going to x with respect to the given measure mu j, but that is support of mu j, right. The essential range of x going to x, that is the identity function with respect to a measure would be simply the support of that measure. So, that is why the support of the measure comes in the spectrum, right, because multiplication by x, the spectrum is the essential range is actually the support of the measure. So, that is how it comes up. Okay. So, I hope the statements are very clear. So, we will continue with the proof. So, we proved one part, right. So, we proved that the spectrum is contained in. So, we already proved that spectrum of A is contained in the support of all the measures, right. So, support of mu n and you take the closure, right. So, we proved one containment. So, next we show that the increase of the spectral resolution, that set is contained in the spectrum of the operator. Okay. So, we show that all those lambda such that for every epsilon positive, E lambda plus epsilon is not equal to E lambda minus epsilon, right. So, this is the increase set, right, or the set where the E lambda is increasing, that is contained in the spectrum. Okay. So, that is what we want to show. Okay. So, let us do that. Suppose lambda naught is not in the spectrum of A, right. So, I am taking something which is in the complement of the spectrum of A. So, I am looking at sigma A complement, I want to show that will be in the complement of the set which is on the left hand side, right. Okay. So, lambda naught not in sigma A, let epsilon be positive such that 0 less than epsilon less than d of lambda naught sigma A. So, remember sigma A is a compact set, lambda naught is something which is not in sigma A. So, the d here means the distance. So, this is the distance from lambda naught to the compact set sigma A, right, divided by 2. Okay. So, all that is, and you will see immediately what is happening, it is not all that difficult to write down these things, but let me draw a picture so that this is a bit more clear. So, the spectrum is somewhere here. Okay. It need not be exactly equal to this interval, it is some compact subset of that, and lambda naught is something which is outside. Okay. So, I keep it slightly away, so that I can draw something, and I have some distance, right. So, I look at, so the distance between sigma a and lambda naught is the distance d, right. So, d lambda naught sigma a we denote by d, and epsilon is much smaller than d by 2, right. So, here I have lambda naught minus epsilon, here I have lambda naught plus epsilon. All right. Now, what I do is I choose an appropriate function. So, define g of x. So, I am going to define a function g. You can make it continuous, but let us see the conditions on g. One, if modulus of x minus lambda naught is less than d by 2, okay, or epsilon, does not really matter. So, here it is 1. So, here meaning in this interval it is going to be 1. Okay. So, that is my g, okay. And 0 if modulus of x minus lambda naught is greater than or equal to d. So, the moment it reaches here, it is 0. So, on the spectrum it is, so you can think of it to be 0 here, and then it is 1 here. So, and make it linear in between, okay. So, and linear otherwise. Okay. So, all I am doing is I am taking a function which is 1 in some interval, 0 in some other set, and making it linear in between, right. So, it is going to be a continuous function, right. So, make sure that this is continuous. Okay. So, here it is 0, here it is 1. Well, what is the big deal? Because it is a continuous bounded function, I know how to define g of a, right. Hence, g of a is well defined, because it is a bounded function and we have the L infinity, well it is actually continuous function. So, we have the continuous functional calculus, and g of a is actually 0, right. Why is that? Because we know the norm of g of a, norm of g of a is less than or equal to supremum over lambda in the spectrum of a, right. All these things we have done in the beginning itself. In the Gelfand-Naimark theorem itself, you know that the supremum of g over the spectrum, right, for a continuous function on the spectrum, supremum over g will be equal to the operator norm of the corresponding image, right. Here well, we can use less than or equal to, in fact, it is equal to, does not really matter, because we are going to get 0 mod g lambda, right. But on the spectrum, so what happens on the spectrum? On the spectrum g is 0, right. So, g of a is 0, right, this is 0. Okay. So, the operator we have constructed is actually 0, right, because the g is 0 on the, so roughly speaking on the spectrum g is 0, and the operator is generally realized as multiplication by x on various L2 spaces supported with respect to measures supported on sigma of a, right. So, g of a will be multiplication by g of x, and that is 0 there, right. So, okay. So, let us continue, but so we, if you look at the figure you will see that, so but so look at here, this is 1, right. So, that is like the indicator function of lambda naught minus epsilon plus lambda naught plus epsilon, but the indicator function is 0 everywhere else, right. It is supported only on that interval, but g is a positive function outside that, sometimes it is 0, but it is still between 0 and 1 in some interval, right. So, the function g of x is greater than or equal to indicator of lambda naught minus epsilon, lambda naught plus epsilon, okay, x, right, for every x, right, because on that interval it is g is also 1, and then everywhere else the indicator function is 0, okay. But so there are couple of things you should notice, that g is positive, indicator function is positive. So, if I look at the corresponding operator, these are all bounded function and we have L infinity functional calculus, right. So, if I give you an L infinity function, a bounded function, you know the corresponding operator, right. If f is bounded, f of a makes sense. So, g, well, g is a positive function. So, g of a will be a positive operator, right. since G is positive, G of A. So, G of A is my operator which is actually 0, but G of A is a positive operator. In particular it is a self adjoint operator, positive operator, and G of A is going to be greater than or equal to chi lambda minus epsilon lambda naught plus epsilon A, right. So, chi lambda naught minus epsilon to chi lambda naught plus epsilon, the indicator function of that interval will give me a projection, right. So, we call that any interval or any set is going to give me a projection, right. So, that is the L infinity functional calculus, right. So, chi lambda naught minus epsilon lambda naught plus epsilon is a projection. Now, what I am saying is these operator G A is greater than or equal to this operator. What does that mean? Well, these are self-adjoint operators. If I have two self-adjoint operators, let us say T and S, T is greater than or equal to S, meaning T minus S is a positive operator, right. So, I need to show that G A minus chi lambda naught minus epsilon 2 lambda naught plus epsilon is a positive operator, right. So, let us write down. This is same as saying G A minus chi lambda naught minus epsilon 2 lambda naught plus epsilon of A is a positive operator, right. So, I need to look at its action on some vector V and take inner product with V and see if it is positive. Okay. So, note that G of A minus chi lambda naught minus epsilon lambda naught plus epsilon A acting on some vector V, inner product with V equal to, well, you can use linearity to write it as G A V V minus chi lambda naught minus epsilon lambda naught plus epsilon A acting on V, inner product with V, right. So, you will get integral G of x minus chi lambda naught minus epsilon, right. That is how the definition is, right. So, lambda naught minus epsilon to lambda naught plus epsilon x, and remember the measure d mu u V V, right, we used V there. So, V V. Okay. But this is a positive function, right. So, this is greater than or equal to 0 because of whatever we have, right. G minus chi is greater than or equal to 0 and this is a positive measure, and so the integral will be positive, right, and that is same as saying this is a positive measure, right. So, this would be a positive operator. Okay. So, what did we prove? We proved that G of A is greater than or equal to this projection, right, but G of A is 0, right. So, hence 0 greater than or equal to. So, now whatever is remaining is very trivial. G of A is greater than or equal to chi well, okay. Yeah, maybe let me write this once more so that this is clear. Chi lambda naught plus epsilon lambda naught minus epsilon A, but what is this? This in terms of the resolution of identity and things like that, we know what this is, right. This is E lambda naught plus epsilon minus E lambda naught minus epsilon, right, and that we know is a positive operator. Right, ES is greater than or equal to ET if ES is greater than or equal to ET if S is greater than T, that we know. That is part of the definition of the resolution of identity, and you should check why chi lambda naught plus epsilon lambda naught minus epsilon A is actually this. Well, why is that? Because the way E sub t will be defined is you look at the projection corresponding to minus infinity to t A, right, that is how the projection was defined. So, because of this G, since G A equal to 0, this is equal to 0, which is same as saying E lambda naught plus epsilon is equal to E lambda naught minus epsilon, right. So, I started with a lambda naught which is not in the spectrum, and what we have seen is that particular lambda naught is not a point of increase for the spectral measure, the spectral projection or the resolution of identity, right. So, hence, so that proves whatever we want. So, let us see what is that we were trying to prove. Yeah. So, hence all those lambda such that E lambda plus epsilon is not equal to E lambda minus epsilon for every epsilon positive is contained in the spectrum of E, right. So, that is how that is one more step. Now the last one. So, we had 3 assertions, we proved the containment of 2, we will prove the third one, and that will complete the proof of the theorem. Okay. So, next we show that, we show that union of support of these measures mu n, and you take the closure, that would be contained in the all those points where the lambda the spectral resolution is increasing. So, all those lambda such that for every epsilon positive e to the lambda plus epsilon is not equal to e to the lambda minus epsilon. Okay. So, we are proving containments in each of the 3 assertions, and then we will put together and we will see that gives us that they are equal. Okay. Okay. So, let us see how to prove this. Suppose, so I take some point lambda naught in the left hand side, and then I prove that it is in the right hand side. Suppose lambda naught is in the support, okay, support of the spectral measures mu n bar. Well, in whatever I am going to write is actually straightforward, but just to understand it, you may think of one measure and then you will see that this is fine. Okay. So, then we can find some phi, okay, not equal to 0 such that, so we can find some function L2 function phi such that phi is in L2 of R with respect to one of the measures, okay, for some n. Okay. Well, let us see what that means. I take some lambda naught in the union of the closure of the union of support of several measures, right. So, if it is in the so it means it is a limit point of some one of those sets. Okay. So, you can think of it like that. In that case, so let us see. So, if this is support of some set, and let us say lambda naught is an limit point. So, that means lambda naught is here, right. So, maybe I did not draw this properly. So, let us draw this again. So, I have this set, and let us say this is lambda naught, right. So, that is like the point in the closure, right. So, if I take some interval lambda naught minus epsilon to lambda naught plus epsilon, there is this portion which is entirely contained inside the support, right. So, our measure mu n will have positive measure there, right. So, I can take the indicator of that part, that will be in L2 and it is a non-zero function, right. That is all I am saying in this this line, that we can find a phi non-zero such that phi will be in L2 for some measure mu n, right. I have several measures there, at least one of them will have this property. Now, that is enough, because then it is easy to see that phi belongs to the range of E lambda naught plus epsilon minus lambda naught minus epsilon, right, E lambda naught minus epsilon, E lambda naught minus epsilon. Okay. Well, why is that? Because, well, this is something which you have to justify, it is not very difficult. Remember this, the measure is realized as a multiplication operator, right, multiplication by x. The corresponding resolution of identity is given by, you look at minus infinity to t, look at that set, look at the indicator of that and look at the projection corresponding to that, right. So, via spectral theorem we know it exists. So, when I look at E lambda naught plus epsilon minus E lambda naught minus epsilon, after realizing the operator as a multiplication by x operator, this would be the difference of this projection is another projection which is multiplication by the indicator of lambda naught plus epsilon minus lambda naught minus epsilon. But phi is supported there and phi is a non-zero function, right. So, this is sort of, so in other words this is equivalent to saying that the indicator of lambda naught plus epsilon lambda naught minus epsilon times phi of x is equal to phi of x almost everywhere, right, as L2 functions d mu n functions, okay, and that is enough, right. So, if I have this, then I know that so well the operator corresponding to this function is my the difference of this projection, right. So, if I look at this, this is same as saying that E lambda naught plus epsilon minus E lambda naught minus epsilon phi equal to phi, right. So, E lambda naught plus epsilon minus E lambda naught minus epsilon acting on phi equal to phi implies E lambda naught plus epsilon minus E lambda naught minus epsilon is not equal to 0, right. So, I started with some epsilon, but whatever epsilon I choose, if I can do this for one epsilon, I can do this for all epsilon smaller than that, right, that is enough. So, all small epsilon if I do, it will be true for every epsilon, right. Hence lambda naught belongs to the set where E sub lambda is increasing, right, or lambda such that E lambda plus epsilon is not equal to E lambda minus epsilon for every epsilon positive. Okay. So, we have completed. So, let me write down all of this again. So, in the first assertion we proved that, so we proved, that. So, I will write down the 3 containments just to see that it is fine, right. So, we proved that in the first assertion we proved that sigma A, that is the spectrum of A, is contained in so maybe I write it in the middle, so that okay. So, sigma A is contained in union and the supremum of the support of the measures and you take the closure of that. In the second assertion we proved that the increasing set for E lambda is contained in the spectrum. So, that is all those lambda such that for every epsilon positive E lambda plus epsilon is not equal to E lambda minus epsilon. So, that is contained in sigma of A, and in the last one we proved that the support, the union of support, that is the right hand side, is contained in the increasing set, right. So, all those lambda such that for every epsilon positive E lambda plus epsilon is not equal to E lambda minus epsilon. Okay. So, because of, so since this and this set are same, all the 3 sets are same. Okay. So, we will stop here. We have written down the spectrum in terms of the resolution of identity, the increase in resolution of identity, in terms of the support of the measures, the spectral measures that come up, and well, they are all equal to the spectrum of the set A. Okay. So, that is what. Okay. So, we will stop here and we will continue with commuting family of self-adjoint operators and normal operators in the next few lectures and prove spectral theorem for that. Okay. So, let us stop here.